So, my name is Alex. I'm developing mobile application over 8 years, and part of my experience is related to cross-platform development, like with Xamarin and C#. And spoiler, it will help me today somehow. But for the last 3 years, I'm concentrating for Swift development. So. For the last time, after the last session, we with Dmitry was discussing what will be good to discuss on the next presentation, on the next meetup. And so we discussed what is going to be new on the Swift 6. And the one part is update for a Swift concurrency, so we decided that it will be nice to get in brief overview about the technology itself. So, the topic is really big, and I understand that it's already evening, and most of us had a long working day. So I'll try to keep it short and fun. Let's go. As for the first slide, you can see this beautiful quote wrote by Chris Ledner in a Swift Concurrency Manifesto. And briefly, it says us that Swift concurrency is not a silver bullet or something, but it's an attempt to solve current problems and build a fundament for the future development of Swift to, like it's written, to further greatness. So our agenda for today. What is Async itself? How it's working and how it's different from GCD, how it solves traditional multi-threading problems that we are familiar about, and which multi-threading problems we are facing now when we have this technology, and some conclusions and revelations, and we ended up with questions. So, what is Async itself? Short answer, it's a pattern that allows concurrent code looks like a serial one. On this slide, you can enjoy the screenshot from a Wikipedia that shows us that the pattern itself is really old. It was introduced in F# back in 2007, and it became a working standard with a C# back in 2012. So like Async await is new only to Swift developers. So then I want to tell that Swift's Async await is actually the same as anyone else. But yeah, this guy tried to give us some that same but different, yeah? So why is it different? Basically, async await is related to the actors. And what is happening when we are trying to await some method of actor is we go into a known executor, which is a default property of the actor protocol. And what this really means that actor going to get our requests, our calls for methods in a serial queue. That actually means that we are not able to call the actor from a different thread simultaneously. So what is the actor specifics by Swift developers? Its specifics that actor allows synchronous access to its members only from within itself. Next, actors allows only asynchronous access to its members from the outside of the actor, and actor allow only asynchronous access to its members, also from async context. And when I saw these specifics for the first time, I mentioned in my memory the quote by Alan Kay that actually his definition of object-oriented is somehow related to the actor specifics. So he says, are you able to read, right? And in the end he says there are possibly other systems in which this is possible, but I'm not aware of them. Now, Dr. Alan Kay, we are aware. It looks like Swift has one that passed good to your definition. So, what we see here is specifics of entity called main actor, and what is most important part here is it implements serial executor. So basically now we see here that the actor is actually a class who implements serial executor protocol and who has some methods to call this executor, and is actually so what I'm trying to say that actors are basically the classes at the end, with just small addition, that is that I said previously, giving us an ability to call it through the queue. So when we are talking about tasks, and when we write in task inside which we going to evade some function, for the compiler it sees like the second slide, which shows us how the tasks are related to the actors and its executors. So basically, when you are writing a task and evade inside of this, it will be compiled in the main actor shared unowned executor and queue, which going to pass our call to the serial queue of the actor. And basically, for us, for our experience, it will be somehow looks like a dispatch main queue async. And as one of important things about executors, again, when I saw the implementation of the executor, I immediately mentioned that it looks really similar to just a command pattern. So yeah, that's it. And you just can compare in your head if it looks the same to you or not. So moving forward, and the second part of our talk is how the Swift concurrency different from GCD. And short answer is Swift concurrency is a higher abstraction layer for threads working aside of GCD, but still call it under the hood. So in order to explain it in a fun and short way, I decided to show you this. So yeah, we have here two Terminator versions. One is T800. This is the old one, so I mentioned it as Objective-C. And the second one is T1000. Here is a newer model, so it's a Swift. What we know about Objective-C, It's old-fashioned, straightforward. It doesn't have any idiot protection. It's just doing what you tell him to do. And so, for example, if you try to reach the 20th element in the array, which consists only 2 elements, who knows what Objective-C will return to you? Basically, he will return what is available on the address, which he calculates as a result of the 20th element of this array. So it can be anything, basically. So what we know about Swift, like a U-turn hater, it's fluid. And by this I mean it's more agile. According to our present life problems, it's pretty optimized. And it's also tries always to look for workarounds. So by this I mean that it's somehow has some mechanisms which allows compiler to prevent developer from stupid mistakes, or even not so stupid. Yeah, but what else do we know about these guys? That both of them are running by Skynet, which I decided to mention as a C. So as far as you know, of course, every part of, not every, but maybe the most, parts of the iOS SDK and its libraries are at the end referencing the C libraries and C code. So as for the Swift, we know that it has some high-level features that is only for Swift. It also implements in own way some features which are available in Objective-C. And also it has some features which are not included in Objective-C, but available for Swift through C. So, and what is important in this in our context today, that the Swift concurrency uses its own part of libdispatch, which was previously used by Objective-C to run Grand Central Dispatch features. So what do we have now? On the top left corner, you see the traditional thread model, which was for a long time before Swift concurrency came out. And down right, you see the model of cooperative thread pool with introducing of structured concurrency. So to keep it short, the most important part here that in traditional thread model, we operating with the threads and actually we should, by switching a thread, by running a new thread, we understand that our device, our CPU should manage all the threads that it has and also manage the resources that are blocked by threads, which is, for example, stack frames, locked resources, and so on, so on, so on. As mentioned by Apple engineers on the WWDC 21, there is a problem of thread explosions, which means that we have more threads than physical CPU cores. And this means that when we are trying to manage them and synchronize them and switching them, we are spending a huge amount of resources on this. Basically, it's like the most expensive operation because it's highly related to a CPU working time. So what do they do with a new structured concurrency model? Is that they said we have so many threads as we have cores. Basically, maybe not, because their second statement is we're going to have so many threads that we need, but as less as possible. So, but let's keep the simple one. Count of threads is equal to count of CPU cores. And in order to keep for us an opportunity to stay concurrent and have more operations than actually we have than actually amount of threads that we have in, they introduced continuation. So in my understanding, the continuation is basically a task that we are having. So the task is like atomic job for a thread that it will do. And instead of switching a context, instead of managing a thread's resources, it now manages only a task suspension and task resources. So it sounds like it's actually the same, but in the same time, it's way more easier than switching the threads. So yeah, just as I said, that task can be interpreted as a continuation, and it gives us an opportunity to keep the thread forward progress, which is also a term from iOS engineers. So yeah, their main idea that the threads should run as fast and as long as possible. And the second thing here is a task is the most convenient and a straight way to show to your compiler that you need a concurrency now. So it's basically the entry point for your concurrency execution. The next step of our journey is await. So what is actually happening when the execution time, when the execution context meets await? Now it's going to ask a question. Is it a suspension point or not? Basically, potentially it's always a suspension point. But what is the most important thing for the guys who didn't met Swift concurrency yet is that in this moment we should remember that we are no longer have any information about the threads. Swift going to decide itself if he goes to suspend the current task on the current thread and keep the execution, keep your like await call on the same thread, or if he decides that it's too heavyweight, it has another priority, or the current thread should run forward, he will be able to get it to the another thread, and you like mostly never, and it's highly unrecommended to you to find out which thread you are using now. Yeah, so the other words for this from the also Apple WWDC 21 that the we have actually our stack, our call stack, and if we decide to, let's say, keep working on a current thread, Swift decide for us to keep working on a current thread, then our previous work, which is here other work 1, will be replaced in the stack by other work 2, and our context, our resources, all that relates to other work 1 will be saved in a heap, and stack goes to switch to the other work 2. Yeah. So far, we go into our third part, and it's about ways to solve traditional multi-threading problems. And the short answer, how Swift concurrency is doing it, is by keeping your filthy hands off the threads. As was mentioned before, you are no longer able to messing up with the threads, so that's why they think we don't gonna have any troubles, more. Yeah, so I guess nobody needs to take long time here on this slide. It's just a list of the commonly understandable multi-threading problems. So let's keep an eye on how it solves it. So the first problem is priority inversion, and for today I don't have for you some long explanation because it's like it's too deep to dig for today. I see your tired eyes, so it's going to be only short answer that partially priority problems are solved just like they was solved in the Grand Central Dispatch, and although there is some mechanisms like a priority escalation in the executors, which allows Swift concurrency to do it under the hood. So, speaking of the deadlocks and thread explosions, we should rewind to our journey to cooperative thread pool and structured concurrency, because itself will prevent our code from deadlocks and thread explosion. With thread explosion, is as simple as it is. We just have so many threads that we have CPU cores, so we are just physically not able to generate the situation of thread explosion. With the deadlocks, again, it's not fully gone. We're still able to do it somehow, but it's not a problem of a deadlocks because it's not a deadlock of threads. Now it could be only deadlock of tasks. But basically, in normal way, using of a task will prevent you from the deadlocks, but as was said, it's not a silver bullet. You are still able to write logical, not so right logical code. Here we should mention one more important thing from a WWDC 21, that Swift engineers don't recommend us, or maybe it's better to say they don't want us to use Swift concurrency mechanisms along with old Grand Central Dispatch mechanisms. And basically, I hope you understand why. But as from my side, first of all, it's like using microwave inside your oven, which is like not so effective and stupid. But also, of course, they are mentioning that as long as a Swift concurrency using the same mechanisms as ground central dispatch, we are able by our interception, we are able to ruin the algorithms that are working with Swift concurrency. So that's why they are, for this time, they are just kindly asking us not to use ground central dispatch mechanisms alongside with Swift concurrency. So speaking of data race and race conditions, we also should rewind back to the understanding of the actors and its specifics, because they are itself preventing, spoiler, not always, they are preventing us from getting into the situation of data race and race conditions. Race condition, again, simply as it is, just as we able only to call the methods of the actors using it through the serial queue, we are not able to get into the situation where several tasks trying to work with actor, and as long as it's isolating its state, so basically it means for us that we are not able to get any variables or get some data that is isolated by the actor. That's how Swift concurrency prevents us from a data race. Yeah, so this is basically the end of the part 3 and our fourth part, which multi-threading problems we are facing now. As I was said previously, Swift concurrency not guarantee to avoid all the problems for the concurrency, and basically introducing a couple of new ones. Yeah, but you know, it's just to keep us safe from losing our work. So we should be thankful for this. And the first problem that I want to discuss here is an actor reentrancy problem. And it's really similar to a data race. Here you have a short example that I just get from the article, thanks to the author. I mentioned him on the end of the presentation. So the pitfall for us in this example is that in this await authorized transaction, what should you learn about this piece of code is that when the compiler, when the runtime meets this await, it decides about the suspension point, and it gives us a pitfall, and that's why. So if we, for this example, call in a code like we're seeing here on the top left, we're trying to asynchronously withdraw 800 and then 500. What we see here is that we checked balance 2 times, and that's why. Because on this await, our first call was suspended, or it goes to another thread, which is give the second call an opportunity to enter the actor and pass the can withdraw method. So this results that we have 2 times check balance, and then we have the problem down there because our check was false. Yeah, it wasn't like checked properly, so now we have balance below 0. Next problem is a thread starvation. Thread starvation is basically about the problem that we are able not to accurately prioritize our tasks, and it can be happen so that some of our threads are going to stay idle while the other, in the worst scenario, the main thread, will keep doing the most of the job. And the things getting worse when, for example, we have our main thread that is, let's say, main actor, who is waiting on some research which is held by the thread 3, like we see on the image, but thread 3 is staying and waiting for the thread 2 for completion, because the thread 2 have like higher priority than the thread 3. So it's not the normal scenario, but it can be so. One more problem that I want to mention that is not so obvious is accidental context inheritance, which means that when we call in some actor, when we executing some task, it's not obvious for us which context it has. And in these cases, we are able to make some mistakes with task cancellation, because some task which is in dips can be cancelled due to cancellation of the parent task. We can do some heavy task on a main thread, because like on the example, our task inherits context of main actor, and so on, so on, so on. So we should be aware of losing our focus on the task context, because it's like it inherits most of the time, and we should be aware of what exactly it's inherit. And yeah, wrote so far. Our 5th part is just a couple of my conclusions. I'll just read it because I'm also a bit tired. So, as was mentioned at the very beginning, Swift concurrency is not a silver bullet, and as from my perspective, is a Swift-like solution for a multi-threading, which is showed up so late only because it was able to be postponed. However, it's a powerful instrument which will definitely help us developers to write more efficient and convenient code. And especially for the sync await pattern is a complex and time-honored solution which has both pros and cons. And if you wasn't familiar with it yet, you shouldn't have any doubts. There is a place for suffering. The task management can be hard, so like prioritizing, cancellation, suspension, continuation of the tasks. Async hell, because like if we are giving async attribute to one of our functions, No doubt, we will add more. Also, as was mentioned, the context of execution, and we can continue this list. Although, in my opinion, it's a way more safe and easy to solve it with a specific abstraction rather than with a wild and wide API, which doesn't give you a chance for mistake. So far, that's all. Thank you very much. Your questions? Yeah, good morning.
Good morning. As you discussed about the concurrency Swift, so there are two methods, async and the sync. Both are used for threading in iOS development. So when we use the sync and when we use the async, is there any rule or the general mechanism to use async and sync vice versa? In which condition we should adopt this?
Do you mean the sync and async for the key use in the Grand Central dispatch?
Yeah, for the dispatch.
Like this.
Let me explain more, because as a developer, it may be more funny. Because when we code, first we write async and we load the table view or collection view. If it is working, we just we just move away. And if it is not working, we move towards the async. Same like in dispatch queue for the main and for the global. So my question is there any standard to follow async and sync for a particular case?
Yeah, basically the big pitfall here is that async and sync for the dispatch queues is not actually the same as global actors for the Swift concurrency. Yeah, like same but different, because global actors they have always serial queue under the hood, and as we know from the slide about actors, actors allow only asynchronous access to the actors members from any asynchronous context, and allow only asynchronous access to the actors members from outside the actor. So basically, there is no chance to do something in the understanding of word sync when we talking about Swift concurrency. So like sync and async is the nice topic about the serial and concurrent queues for the Grand Central dispatch, but it's totally not relevant here.
Here's another one.
Of course.
You talk about the deadlock. It occurs when a particular resource wants to utilize some resources that is being utilized by someone else. Is it the dependency? The deadlock occurs when the one party wants to use the resources of the other party that is being executed or in process. That's why deadlock occurs. This is the definition of deadlock.
For sure.
Okay.
Yeah.
So if we have a multiple threading task that is being executed, and meanwhile the second task or second thread want to use the same resources, what would happen?
Yeah, actually, it's again about the actors, and if everything is done right, then your new task will be suspended in the serial queue, which we call executor. Yeah, here you can see on the screen that our call to heavy data load, it goes to the unknown executor, which is only property of the actor protocol. And basically what doing unknown executor is only enqueuing the calls to our actors. So I guess short answer, your task, which is potentially goes to wait on the resource which is held on the first task, will be suspended in this queue. And actually, it's kind of, we can say, mutex, because our task, our new task, wasn't able to get into the critical section, which we call in now actor method.
Don't you think it would crash the application?
There is also always a chance to crash the application. that's why I mentioned in the very beginning, if you've done everything right, because of course there is a situations especially with multi-threading, where you are able to crash the application. But what is, in my opinion, what is Swift engineers doing by implementing the Swift concurrency? They want us, they want to make it harder to crash the application because of the concurrency. And also, I have an expectations that with time they are going to do it on a compiler level. So like they will be force compiler to understand our code better, analyze it, and saying that there is some potential concurrency problems, just like it was before. Yeah, we already have some issues where compiler tells us, like mommy, that there is potentially race conditions. But yeah, that's what they done in the Swift 6. They do some corrections about these mechanisms because it was telling us too oft. So yes, please.
In one of the first slides there was a main actor and there was final main actor, and I was wondering, you can't yeah, this one, public final actor. Why is it final? You can't subclass an actor, can you?
Of course, but not the main actor. Main actor is one of the global actors. So like actor is basically the protocol, and but this is implementation of the main actor that we are able to see in the sources.
Yeah, I know, but I mean the blue word, actor, which is a kind of a class which can't be subclassed, and therefore I was wondering why there is the final keyword.
So yeah, just like I mentioned.
Does it compile?
I guess because it's the sources. It's not the code written by anyone or me. It's just from the sources. It's decompiled.
Let me give you the answer.
Yeah.
Actually, when we don't want to inherit the class with someone class, we use final keyword.
Yes.
So this is our main actor. We don't want any class to inherit from this. So that's why they use final keyword.
But you can't inherit from an actor.
I have an answer. There is somebody from the Swift team saying that they decided not to allow inheritance for actors, but in future it might be a possibility, so they decided to allow
Okay.
it to happen in future.
Okay, thank you.
Yeah. So
It doesn't have a meaning now, but it might have in the
Yeah.
future.
yeah, and as far as I know, there are also opportunity to write custom actors, which is actually do not recommended by Swift engineers, because let's say by iOS engineers, because they think that for iOS development is enough to have two basic actors, basic global actors. And we shouldn't provide any custom global actors, but we are able to.
Can I
one more time, please.
The multi-threading is a atomic activity. This is not non-atomic in respect of Objective-C. It do not create a.
Of course, task can be suspended.
Yeah.
That's why they don't write the task on this slide, rather the continuation. This is the difference between the task itself and continuation, that our task could be suspended. But again, just from my perspective and for easier understanding, I'd like to say that the task, if it shouldn't be braked during the execution, should be understood like atomic job. Yeah, so if we don't need current thread to suspend, to switch, to change the context or anything else, it will just do the task and returns to the await after execution. So that's why I mentioned that task is basically somehow can be interpreted as a continuation.
So my question is, don't you think if we use multiple threading at multiple times in a single project, it will create load on our memory optimization?
What it will do?
Should I repeat? If a developer uses multiple tasks or multiple threading in a single project at a time, don't you think it will create a load on memory or the CPU, or how you can deal with the memory optimization at that?
If I understood the question correctly, as for this reason, they actually done the Swift concurrency. Because previously, when you've done your concurrency, your multi-threading with GCD, you was able to spawn like 15,000 of threads, and it led to the situation when the CPU was only responsible, was only having resources to manage those threads, and that's all. That's what they call thread explosion. As with a Swift concurrency, when we no longer operating with threads, we are actually not able to violate somehow the CPU resources. For operative memory, for RAM, maybe it is possible, but again, there is hard to give a developer a mechanism to do something concurrent and in the same time give him some frames to prevent him from violating the system resources. So as long as we stay in our current situation, you are able somehow to violate the memory, or maybe there is other potential issues for the multi-threading and consequences. But as what I understood from the Swift concurrency, that it will be way more harder for a developer to violate system through the multi-threading with a task, because with straight access to threads, it was way more easier.
Let's maybe wrap up on this. We could still discuss the stuff, but not like on the stage.
Okay, thank you very much, guys.